All right. In this video, we study some set operations. Using set operations, we can derive a new set from existing sets, like combining two sets or taking the common elements between two sets, and so on. And you will see that there is some similarity between set operations and logical operations. In fact, we define set operations in terms of logical operations. So if you are not still familiar with formal logic, please review the respective videos. Okay, let's start. All right, so the first set operation we define is union. Okay, we write like this. So let A and B be sets, then A cup B, we call it, this is the symbol of union operation, is defined as follows. It is a set of elements X where X belongs to A or X belongs to B. Remember, this means logical or. Okay. So graphically, this means this, like this. So if we have set A and B, then the union between A and B is everything that are contained in either A or B. Okay, so this is A cup B or A union B. For example, if we have a set A as 1, 2, 3, and set B as 1, 3, 5, then A cup B is all elements that belong to either of these two sets. So that will be 1, 2, 3, and 1, 3, 5, and 1, 3, 5. But in the set, we must not have redundant elements, so we do not include this one and this one because 1 and 3 are already there. So this should be 1, 2, 3, and 5. Okay, so this is A cup B. Next operation is intersection. Intersection. That we write like A cap B. So this is an upside down union symbol, and we usually call it A cap B because this symbol looks like a cap on your head, right? And this is defined as this. So it is a set of elements X such that X belongs to A and X belongs to B. Okay, so remember this symbol represents logical AND. Okay, so graphically this means this. Okay, set A, set B. So elements of A cap B belongs to both A and B. So that means this region represents the intersection. Okay, again, let's see an example. Let's use the previous example. A is 1, 2, 3, and if B is 1, 3, 5, then A cap B is, so all elements that belong to both of these sets. So that's 1 and 3, right? So it's 1 and 3. That's the intersection. Okay, next, using the notion of intersection, we define the notion of disjoint sets. Okay, and we say A sets A and B are disjoint. Disjoint sets. So that means, definition, if their intersection is the empty set. Okay, so that means these two sets A and B have no elements in common. So their common part is empty, no elements. So in that case, we say A and B are disjoint, or they are disjoint sets. All right, now consider addition and multiplication between numbers. Okay, so if x and y are real numbers, then we know that x plus y is equal to y plus x, or x times y is equal to y times x. So that means we can swap the order of addition or multiplication in any way, right? And this property is called commutativity, or we say addition and multiplication between real numbers are commutative. Okay? And just like addition and multiplication of numbers, we also have commutativity between union and intersection of sets. So let's see that. We introduce that as a lemma. Of course, A and B are sets, assumed to be sets. Then we have A cup B is equal to B cup A. And similarly, we have A cap B equal to B cap A. So, can you prove this? All right, so how do we prove this? Before proving that, let's recall what we mean by two sets being equal. Okay, so here A cup B is a set and B cup A is another set, and they are equal. So what this means is that, let's go back to the definition of the equality between two sets. That means A cup B is a subset of B cup A, and B cup A is a subset of A cup B. So one of them is a subset of the other, and vice versa. So if both are subset of the other side, then they are equal. Then this means A cup B is equal to B cup A. So what we want to prove is this subset relation and this subset relation. If we can prove both, then we prove this. Okay? Okay, so now first consider, let's prove A cup B is a subset of B cup A. So how do we prove this? What does this mean? That means every element of A cup B, so if AX belongs to A cup B, then that X, the same X, is also an element of B cup A. So that's what we need to prove. Okay, so let's assume this. So suppose, start from here, suppose X is an element of A cup B. Then what does this mean? So according to the definition of A cup B, this means, this implies X belongs to A or X belongs to B. Okay? But, this is logical OR operation. This is commutative. Okay? It can be validated by writing the truth table of logical operation. So if you write like this, A, B, truth table, true, false, false, true, false, false, and A or B, and try B or A. Okay, so this is true, true, and this is true, true, and this is true, and this is true, and this is false and false. So that means these two propositions are equivalent. So That means x belongs to B or x belongs to A. So this means x belongs to B cup A. So therefore, A cup B. So every element of A cup B is also an element of B cup A. B cup A. Okay. Now we need to prove the opposite subset relation. This one. Okay. Now assume this: x belongs to B cup A. Then that means x belongs to B or x belongs to A. So this arrow goes backwards also. And similarly, this can go backwards. So if this is true, then this is true. But if this is true, then this is true. Therefore, we prove that these two sets, B cup A is a subset of A cup B. Therefore, A cup B is equal to B cup A. Okay? And we can prove the second one. So the commutativity of intersection can be proved in a similar manner, and you should try that yourself. Okay, again, consider addition and multiplication between numbers. So for numbers, we have this property: x plus y plus z is equal to x plus y plus z. Okay, what this means is that we first add y and z, then to that we add x. And that result is equal to this right-hand side, which is obtained by first adding x and y, and then to that we add z. And similarly, for multiplication, we have x times y. Z is equal to x, y times z. So these properties are called associativity, and we say addition and multiplication between two of real numbers are associative. And a similar property also holds for set operations. That is union and intersection. These set operations are also associative. So let A, B, C be sets. Then we have A cup, B cup C is equal to A cup B cup C. And also A cap B cap C is equal to A cap B cap C. Okay, so proving this is an exercise. Okay, so as we have done in a previous lemma, in order to prove that two sets are equal, we need to prove subset relations in both directions. Then we are done. Okay, and so I'll just give you a hint. So first assume that x belongs to A cup, B cup C. Then from this you derive that x also belongs to A cup B cup C. And you can go in the opposite direction in a similar manner. Then we are done. Okay? So because of these properties, we can take set unions in any order. So for short, this can be written as, so instead of writing this or this, since they are the same thing, we just write A union B union C, or A cup B cup C. So this or this, it can be written as just this without any parentheses or brackets. And similar for this one, intersection. By the way, the same convention also applies to addition and multiplication of numbers. Because of this property, we just write x plus y plus z without any parentheses. Or for this, we just write x times y times z without any parentheses, because these are the same thing. And that simplifies some notations as long as there's no confusion. Next, let's turn to the distributive law of numbers. So for numbers, we have x times y plus z is equal to xy plus xz. So this is called distributive law. And we often say multiplication distributes over addition. Okay, and a similar but slightly different distributive law also holds for set operations. And that is, for set A, B, C, we have A cap B cap C is equal to A cap B cap A cap C. Also, we have A cap B cap C equal to A cap B cap A cap C. So in this case, intersection, we can say intersection distributes over union, and union distributes over intersection. Okay. By the way, this one, the distributive law of numbers means first we add y and z, and to that we multiply x. Okay, then we get the result that is equal to, first we multiply x and y and x and z and add them together. Okay, so this is the distributive law of numbers, and similar law holds for set operations like this. So so far it seemed like we had some correspondence between set operations and number operations, right? Like union is similar to addition, and intersection is similar to multiplication. But the multiplication, the distributive law corresponding to this one does not exist for numbers. For example, x plus y times z is not equal to x plus y times x plus z. So this type of distributive law doesn't hold for numbers, but it does hold for sets. So in mathematics, it is often useful to compare the similarities or differences between new concepts and the concepts you already know. In this case, we had distributive law and commutativity and associativity. So they are all similar to the corresponding operations with numbers, but there is some difference, such as this distributive law. Okay. And we compared union with addition and intersection with multiplication. And this analogy can be understood even better if we consider the operation with empty set. Okay, in the case of numbers, for any number x, if we add 0, then the result is still x. And if we multiply x by 0, then the result is 0. Okay? And similarly, for any set A, if we take union with A and with empty set, then the result is A itself. And if we take intersection between A and the empty set, then the result is the empty set. So this is very similar to the case of numbers, right? So the analogy between union and addition and intersection and multiplication is quite good. Of course, there are some exceptions like this one, but it's still good to know this analogy. Anyway, let's prove this lemma. Okay, this one. Okay, first consider this one, and again, we want to prove the equality between two sets. So first start from here. Suppose X is an element of a cup empty. Then this means X belongs to A or X belongs to the empty set. But this one is always false. So that means this can be true if and only if X in A is true. Okay, so that actually this is equivalent. So if and only if, and this means X. So X belongs to A. So that means A cup, the empty set, is a subset of X, subset of A. Okay, and but this one also means this. So actually, the inclusion also holds for the opposite side. So therefore, these two sets are actually equal. Okay, and you can prove similarly this equality. You should try that. Okay, next we go into another set operation, that is set difference. So this is like a subtraction of one set from another set. Okay, so A and B, let them be sets. And we write A set minus B, so this is backslash. A minus B is defined as elements X that belongs to A and X does not belong to B. Okay. So graphically, it looks like this. So we have A and B. So X belongs to A, but not B. So that means this part. So this is the part where elements belongs to only A, but not B, or anything else. Right? So this is A set minus B. By the way, this one may not look very much like a logical operation, but you can rewrite this as this: logical negation of X belongs to B. So this means X belongs to B is not true. Okay, so negating X belongs to B means this. Same thing. By the way, just like subtraction is not commutative. For numbers X and Y, X minus Y is not equal to Y minus X, right? So similarly, A set minus B is not equal to B set minus A, because B set minus A would be here. So it's completely different from A set minus B. So this part is B set minus A. Okay, in mathematics in general, it is often convenient to consider everything we consider in mathematics is an element of some set. Let's call that set a universal set. Okay, and let's write U, the universal set. Universal set is a set that contains everything we need in mathematics. So such as numbers, or maybe functions, or whatever, figures or whatever. And so if we consider this universal set, we can define set complement. That is set complement. Okay, so that is defined as this. If A is a set, any set, set complement. So A complement of A is defined as the set difference between the universal set and A. So universal set is the kind of universe we consider in mathematics. Okay, everything we can deal with in mathematics is in U, the universal set. And if A is here, then the complement of A is everything but elements of A. So that is this part. Okay, everything in the universe except for those in A. So this is A complement. Okay, so A complement. And for complement, we have the following interesting property. A complement and its complement. So complement of A is equal to A for any set A. Okay, so let's prove this lemma. First of all, A complement is by definition the set difference between U and A. And the definition of the set difference is this. It's a set of elements X, and X is an element of U, and X is not an element of A. Okay, by the way, this can be also written as X, and X belongs to U, and not X belongs to A. Okay, now next we want to consider A complement. So what does this mean? So according to the definition, this is, so now we consider the complement of A complement, this one, right? So U set minus A complement. So by the definition of set difference, this is X belongs to U and X does not belong to A complement. Okay, and let's rewrite this as X belongs to U and not X belongs to A complement. Okay, now let's consider this part. So not X belongs to A complement. But A complement, so this is equivalent to not, so X belongs to A complement means X belongs to U and not X belongs to A, right? So this is the, according to the definition of A complement, we have this, right? And this is equivalent to, so we have this proposition and this proposition combined with logical and everything is negated here. Okay, so by using the De Morgan's law, we have not X in U or not X in A. Okay. By the way, by the definition, the very definition of the universal set, x always belongs to u. So this is true. So if this is negative, this is false, right? So this part is false. So so this or comes here, and negation becomes positive statement. So that means x belongs to A. Okay? So false or this statement is equal to this statement, x belongs to A. Okay? So if this is true, then this is true. So they are all equivalent. So that means this statement is equivalent to this statement. Okay? So we can replace this one as x belongs to u and x belongs to A. But x belongs to u is always true by the very definition of u, because u contains everything we need and x is part of it. So this is always true. So we can just remove it from this and connection, and the result is x belongs to A. So that is A. Okay. So A complement is equal to A. As you can see, set complement acts like very similarly to logical negation. And in fact, we have the set theoretical version of De Morgan's law as follows. So A cup B, if we take the complement of it, then we have A complement cap B complement. And similarly, A cap B complement is equal to A complement cup B complement. And you should try to prove that. And these are set theoretical version of De Morgan's law. Laws. Okay, so the logical equivalent versions of these equalities are follows. So in this case, A, B are sets. Now we consider A and B are as propositions. Okay, so A or B, if we negate it, then we have this is equivalent to A negation or and negation of B. Okay, so this was De Morgan's law for propositions. And similarly, the negation of A and B is equivalent to negation of A or negation of B. So this one corresponds to this one, and this one corresponds to this one. So cup corresponds to logical OR, and cap corresponds to logical AND. So if we take complement, cup becomes cap, and cap becomes cup. And if we negate the logical statement, cup becomes cap, and cap becomes it's not cup. Or becomes and becomes or. Okay. And you should try to prove that. By the way, a set can contain other sets as its elements. For example, this set containing 1, 2, and the empty set, and another set containing only 1, and another set containing 1, 2, 3. So this is a valid set. So this is not a set, this is not a set, but the empty set is of course a set, and this is a set, this is yet another set. So anyway, this is a valid set, and for every set A, so any set A, we can define the set of all subsets of A, and that is called the power set of A. So power set of A is defined as this. Powers of A is some element, and that is a subset of A. Okay, so this is the set of all subsets of A. And sometimes power set is written as 2 to the power of A. So the reason will become apparent later. Why do we use 2? Why is 2 is so special? Anyway, maybe this definition may look a bit too abstract, so let's consider a few examples. Okay, let's see an example and consider A consisting of 1 and 2. So what is the power set of A, this A? So first of all, the empty set is always a subset of any set. So the empty set should be an element of power set, of any power set actually. And then of course, the set consisting only of 1 is a subset, and 2, this is also a subset, and A itself is a subset, right? So there are no other subsets. So we have 4 elements in the power set of A. Empty set, 1, 2, and 1, 2. Note that we have 2 elements in A and 4 elements in power set of A. Okay? Remember this. Okay, so the cardinality of A is 2, and the cardinality of the power set of A is 4, which happens to be 2 to the power of 2. Okay, is this a coincidence? Let's see. Next example, consider B consisting of symbols A, B, and C. So what's the power set of B? That is, of course, the empty set and the set consisting of only 1 element, A, B, and C, and the subsets consisting of 2 of the elements. So let's say AB and BC and CA. And what else? So the subset that is actually B itself. So these are the only subsets. So there are 3 elements in B. So the cardinality of B is 3. And what's the cardinality of its power set? 1, 2, 3, 4, 5, 6, 7, 8. So the cardinality of P of B, the power set, is 8, which happens to be 2 to the power of 3. So it looks like this 3 is equal to this 3. And the previous example, this 2 is the same as this 2. And as long as the set is finite, you always have this relationship. So in general, if the cardinality of A is n, then the cardinality of its power set is 2 to the power of n. You should make sense why this happens. Okay, this is an exercise. And another exercise, what is the power set of the empty set? What is it? Okay. Okay, next we consider yet another way to combine multiple sets to produce a new set. That is Cartesian product. Okay, so let's say A and B are any sets. Then the Cartesian product between A and B, denoted as A times B, is defined as follows. So it is the set of pairs A and B, where A belongs to, lowercase a belongs to A, the set A, and the lowercase b belongs to the set B. Okay, this parenthesis A comma B, this is called an ordered pair. Ordered pair. So this order matters. So A, B is not the same as B, A. Okay, and we use round parentheses. Okay, round brackets. Don't use curly brackets or square brackets. This is just a convention, but in order to avoid any confusion, let's stick to this convention. Okay, so this is an set of ordered pairs. And we've been using this notation all the time when we study geometry in two-dimensional space, right? So x coordinate and y coordinate, and each point is written as something like x comma y and closed by parenthesis. So this is actually the entire space here, entire plane is the set defined by this. So in that case, we were considering the Cartesian product between the set of real numbers with itself. Okay, so this is the Cartesian two-dimensional Cartesian space, coordinate space, right? So x belongs to R and real numbers, and y belongs to the real numbers. Okay, so just like this. So if A and B both happens to be the set of real numbers, we have this set, and which is the same as the two-dimensional Cartesian space or plane. And when we compare two pairs, so let's say we have a pair AB and we have another pair CD, if they are equal, that means they are equal if and only if A is equal to C and B is equal to D. So if the first element is the same and the second elements are the same, right? So if this happens, then this, and vice versa. If we have three sets, let's say we have A, B, and C. So we have defined A times B. So this is a set, right? The Cartesian product between A and B is a set. So with this set, we can make a Cartesian product with C. So that is defined as this. So the Cartesian product, this product is defined for two sets, between two sets, right? So this set is a set of pairs, let's say AB. And this is a set of some elements, let's say C. Okay, so this is yet another ordered pair where A, B belongs to A times B, and C belongs to the set C. Belongs to set C. Okay. And similarly, we can define another Cartesian product in this way. So first, we make the product between B and C. Then with that, make the product with A. Okay, the order matters. So in this case, we could write like this: A and B, C. So this is a pair, and as a whole, this is a pair. Okay, and A is an element of A, and BC is an element of B times C. Okay, but this set and this set, so technically they are different, because for the first set, the first element is a pair of A and B, right? And the second set here, the first element is just A. Okay, and the first set, the second element is just C, and the second set, the second element is a pair. Okay, so they are different. But we have one-to-one and onto correspondence between these two. Okay. We call it isomorphic. So these two sets are isomorphic. In a sense, they have the similar shape. Okay, essentially the same shape. So although they are technically different, we consider them as equivalent. So we write this set as equal. It's not actually equal. We should write something like this. It's similar to A times B times C. Okay, so together, since they are almost the same, we just write A times B times C. Okay, and its elements are written like A, B, C. So it's a triple. It's an ordered triple of elements where A belongs to A, and B belongs to B, and C belongs to C. So we can simplify the notation a little bit. Okay, so these are ordered triple. And we can continue this as long as we want, as much as we want. So let's say we have sets A1, A2, and so on up to AN. So we have n sets, and we can define the Cartesian product of these n sets. So A1 times, A2 times, and so on times AN. Of course, the element of this product is something like this, A1, A2, and so on, AN. So it is an ordered list of n elements. So we call it ordered tuple, or simply tuples. Ordered tuple, and where AI belongs to AI, where I is from 1 to and up to n, right? So since there are n elements, we sometimes call it n tuple. So n tuple. Okay, so the order matters, okay? So if the order is different, it's a completely different thing. And if A1, A2, and so on, they happen to be all the same set. So let's say A times, and so on times A. And we multiply the same set A n times. This is often abbreviated as A to the power of n. Okay? So again, the Cartesian space is an example. So R square is something like this. xy and x and y are elements of real numbers. So this is a two-dimensional plane. And R3 is three-dimensional space. X, y, z. And x, y, z are all real numbers. And so on. In a similar manner, we can define n-dimensional Cartesian space. So x. So we don't have n letters for arbitrary n. So let's write x1, x2 up to xn, where xi is a real number for all I, from 1 to up to n. Okay, that's all for this video. See you later.